una laptop Can you first slide from the yeah, that was color mic So we have our second tutorial talk or invited talk by Professor Richa Singh of Indian Institute of Technology, Jodhpur, entitled Adventures and Impact of AI in Face Recognition and Deepfakes. To chair the session, I would like to call upon stage Professor Bhabatosh Chandu of Indian Institute of Information and Technology, Kollani, to please come up on stage and chair the session for us. Thank you.
Okay. Yeah. Okay. So. Good afternoon, everyone. It's my pleasure to introduce Professor Richa Singh from IIT Jodhpur. She is also adjunct professor of IIT Delhi and West Virginia University, US. Okay. She did her PhD from West Virginia University, USA, and her research interest basically covers pattern recognition, machine learning, and biometrics. On her absolute right, she has co-edited the book on deep learning in biometrics and has delivered keynote lectures and tutorials in several top layer conferences. I just named one or two: BioSec 2021 and ICCB 2017. She is a IEEE fellow of IAPR, and is a senior member of ACM. She has received the Mohandas Pai Faculty Research Award at the IIT Delhi and FAST Award by the Department of Science and Technology, and several best paper and poster awards from many international conferences. Currently, she is serving as the program chair of CBPR 2022, and sorry, it's not currently, it's a 1 year back. Anyway, and is a general, she was a general chair of APG 2021. She is also vice president of publication of the IEEE Biometrics Council and an associate editor-in-chief of Patent Economics. She is also the associate editor of many other international journals. So I welcome Richa to deliver a interesting talk, and I hope she maintains that time because we are running a little short of time. Okay, Richa, please come over. It's your stage. I'll-
Thank you very much, Professor Chandra, and thank you all for the so I'll be talking about adventures and impact of AI in face recognition and deepfakes. These are the two areas that I've been working for quite some time, and I co-direct this image analysis and biometrics lab at IIT Jodhpur. And this lab is particularly working in three areas: AI for security, AI for social good, and trusted AI, with focus on locally connected and socially relevant problems. When we talk about socially relevant and locally connected problems, we cannot miss the 17 sustainable development goals that have been set up by the United Nations, right? In particular, I'm working in three different specific goals in this area, which is good health and well-being, life on land, and peace, justice, and social equality. And today I'll be talking about the 16th goal that is related to peace, justice, and social equality. So biometrics is something like Professor Chandra mentioned, biometrics is something that I've been working for a while. So how can biometrics help in SDG, right? The 16th goal of United Nations, they say that all people will be able to obtain a legal identity. Now, it's when we say that all people should be able to obtain a legal identity, it's not just giving them an identity, issue an Aadhaar card, issue a PAN card, which has a biometric identity enabled with it. But the more complex problem that comes with it is they should be able to use it in all scenarios. And when we say all scenarios, it's constrained as well as unconstrained, right? Take an example of face recognition. All of us have, I'm assuming all of us have Aadhaar today. When we took Aadhaar, when we applied for Aadhaar, we gave face, fingerprint, and iris images, right? Now, whatever data or information that we give, what was the purpose of it? We should be able to use these features, this identity information that has been provided to us in real-time setups, right? So we talk about face recognition, which is one of the modalities. It's the most universally available as humans. We utilize it the maximum, right? So I have been trying for past 2 decades to work in face recognition and make it accessible and workable for everyone in all different kinds of scenarios. Now, there are three things that we do with face recognition: authentication, identification, and utilize it for surveillance, right? Authentication is nothing but a one-to-one mapping, confirming that I am Richa, right? So that is simple. Or identification is identifying who I am. So if I give you my face image and you have a large data of face images, you have to identify who am I, right? And surveillance, we all know, good or bad, whatever it is being used, and we're talking about it, right? So in constrained setups, in terms of identification and authentication, we have very good algorithms already in place. In the last presentation, we already, one of the participants already alluded to the very high performance of face recognition, right? But that performance, that very high performance, is today in constrained setups with cooperative individuals. The moment we come to non-constrained setups, unconstrained setups with non-cooperative individuals, I'll show you the performances where we stand and some of the challenges that are associated with unconstrained conditions or real-world adverse conditions are occlusion. So during COVID, many of us were wearing face masks. All of us were wearing face masks, in fact, right? And we were even uncomfortable in tackling surfaces for authentication, like fingerprint, or putting an iris camera very close to our eyes. So how do you actually recognize a person? And The problem with using faces was the person was wearing a mask and you couldn't ask the person to remove your mask, right? So there could be occlusion due to mask, due to sunglasses, scarves, hats, any of these accessories. We could do long range face recognition where there's a camera placed at a distance and you want to recognize. The problem that comes with it is the face image size that gets captured at a long distance is very, very small. Sometimes even to the size of 8 cross 8, 16 cross 16. That is something we term as long range or very long range face recognition. And when the template itself is of the size, let's say 250 cross 256 cross 256, 512 cross 512, you have to mark it with a 16 cross 16 image. So there's a lot of difference in information inside. Then we have post variations, which will be very common when you have unconstrained setup. And then illumination variation will obviously be there, right? So these are some of the real world adverse conditions which pose. So these are the practical challenges. And in terms of research challenges, the challenges would be occlusion detection because you have some occlusion on your face. You'd have occluded face recognition. In presence of all of these challenges, you need to come up with features which are discriminating in itself, right? Which could discriminate, which could help with our measures of interclass and intraclass similarities, and then low resolution disguise face recognition. And because all of these systems that we come up with have to work in real world conditions in different setups, it is very important to ensure that there is ethnic diversity. System should not be tied to a specific ethnicity or to a specific gender, race, any of these, right? So we started working on this a few years back. And the first thing that we realized is there's no large scale database that is available to be able to solve the problem, right? With today's machine learning approach that we are following, data set is a must. You cannot work without a large data set, right? So the first thing that we did was we created a data set called as the DLOD data set. Now, DLOD is the first of its kind data set in the community. It contains all Indian face images. It's captured in collaboration with DRDO AI Labs set up in Bangalore. And what it contains is face images captured at a distance of 5 meters to 15 meters. So there's a person, there's a surveillance, what happened? There's a surveillance camera setup that is there where a person is walking from a distance of 15 meters towards the camera. And we close the capture at 5 meters. And this capture is done with different kinds of accessories as well. So monkey cap, wigs, sunglasses, hats, caps, all of this, including a high resolution image itself. So it has a significant diversity in terms of occlusions, resolution. In total, 1.2 million face images, 14,000 plus videos of 2,100 individuals specifically. Low and high resolution images with occlusion. Now, since there were a lot of occlusions as well, we thought in order to be able to learn this, we need to annotate this as well, and we need to learn where these occlusions are. So we went ahead and annotated all the occlusions that were present in the data set also. Right? Now, in order to benchmark, the data set was collected and we wanted to check where is the performance. So when we actually check the performance with state-of-the-art face recognition detectors as well as matchers, interestingly, we saw that when the distance is closer, it's 5 meters, the detection performance is close to 90, 91, and 96%, right? Now, interestingly, even at a smaller distance, the detection performance is not 100%. Reason was occlusion, right? Because in face detection, we focus a lot on the eye regions and some other regions. If you have sunglasses or other kinds of accessories which are occluding key facial regions, detection could work. So we have 90%, 91%. Now, if you have 90% detection performance, the recognition performance certainly will go down, right? Because you're only working with detected faces. And in terms of recognition, so this table here at the bottom shows you the performance of recognition of the matches, right? And look at the values. So at 5 meter, we are 79%, 53%. These are at different false accept rates. So these values, all of these values are genuine accept rates at a specific false accept rate. That is how we calculate in the ROC curve. Right? So at 1% FAR, we have 79%. But when you reduce the FAR, it's 53%. And as you go down, as you increase the distance, the performance drops to as low as 19%, right? Now, this is your arc face, and then you have elastic face. So live CNN doesn't work at all. The performance is really, really bad. But between arc phase and elastic phase, interesting thing that could be observed is one of them works reasonably okay at with distance variations, whereas the other one works better with occlusion, right? But when you put both of them together, both of them don't work. So the accuracy drops to as low as 12%. Now elastic phase is doing good, reasonably good at 1% FAR, which is 97.5. But the moment you increase the distance, it's 12%. And I'm just talking about 15 meters. There's a current IRF which is called as Parai, which is talking about phase difference of 500 meters. Right? And I'm just talking about 15 meters here. So look at the gap in the performance that is. It just would not be much. Right? So in order to address this problem, what we did was we came up with an recognition algorithm, which is termed as SegDGD net. Now, what the SegDGD net does, this is a high level idea of SegDGD net, is if you have occlusion on the face images, the very first thing is you need to remove these occlusions. Right? These occlusions cannot contribute to face matching, right? But once you, and these occlusions are inconsistent. With the accessories, the occlusions can vary. And even the impact of these occlusions can vary depending on the or it is a low resolution. Right? So what we did was we learned an algorithm, we created an algorithm to first detect the occluded regions. Now remember previously we had annotated the occlusions, so we have the ground of the occlusion, we could learn a detector to identify where are these occlusions. And then once you identify the occlusions, these regions can be discarded. And then the remaining facial region, which is useful for facial, can be used for recognition. Simple enough, right? But then among the regions that are actually available for recognition, what do you focus on? In this case, if you take a look at the top image here, only the eye region is left, right? You have these black hairs, which are very not useful because right now the person is formed in this manner. In any other image, the person might be formed in a very different manner. So that region cannot be useful. There's eye region which can be used. Now, how does your algorithm figure out for which image, which region actually to use for recognition once you have discarded the occluded regions? So this is a high level perspective of SegDGD. Now, the motivation for this algorithm actually started from dropout. Now, all of us know what is dropout, right? Very simple concept. You drop the notes which are not useful for recognition or something, right? So in 2019, my group had published a IIIT paper which talked about guided dropout. So what is guided dropout? Guided dropout says that you can, rather than randomly dropping or dropping the low performing notes, we introduced the concept of dropping the high performing notes. That is very counterintuitive, right? How does dropping the high performing notes help you? So the way it helps us is if you drop the high performing notes and in different iterations, what it does is learning the loss functions, it helps in improving the low performing nodes, the strength of low performing nodes. Because deep learning, in a way, there have been a lot of names used that it's shortcut learning, or once you achieve a certain level of performance, the other nodes need not perform that well, right? So once you drop the high performing nodes, then you can make the other nodes, which are some of them which might be equally good, to improve the performance. So that was our concept of guided dropout that we proposed in 2019. So we proposed a similar concept, motivated from that for this SegDGD. So the first one was this learning an encoder-decoder network for predicting these masks, right? Where these occlusions lie. So for that, we just used the dice loss to predict the masks, and these are the outcomes of the mask. So this is a segmentation problem where we have input image is this, and this is the ground truth which was given with the annotated data, and the task is to predict the segmentation mask. Now, if you take a look at different, these are low resolution images and these are high resolution images input, and these are the ground truths. And these are the performances given by different kinds of segmentation algorithms. So segment, fully connected network, and all of them. And what you can observe is that the segment consistently, irrespective of the low resolution or the high resolution, does reasonably well job. And these are the results of the occlusion detection algorithm. So with Segnet, in all of these cases, whether it's sunglasses, masks, or it performs reasonably well. Now, what we did next was we took this detector and integrated with the complete end-to-end pipeline for learning the face recognition matter. So we have this disguise detection module. This disguise detection module is integrated with the complete network of face recognition. Now here what you have is we have this PSD layers, and these PSD layers are essentially the pixel strength detector. The AAA idea that I was talking about, guided dropout, this is the guided dropout idea where we learn the strength of every pixel in different iterations and try to improve the strength of different pixels in different iterations so that more and more pixels can contribute to learning. So even if more of the pixels go away because of occlusion, we can work with the remaining one. So this is the broad idea. This is the entire network that we train. So we have this pixel PSD, we have a feature extractor, we have this disguised guided dropout, which is kind of dropping the layers that we are interested in, which are actually occluded. And overall, we use a contrastive loss, and this works with a low resolution disguise probe as well as with a high resolution disguise probe. Because when you get the image, you're not really sure whether you're getting an input image which is of low resolution or high resolution. So whatever model you come up with should work across, right? So this is the network that we trained, and these are the results on the DLOT dataset that we had originally created. Now, like I said earlier, the light CNN, arc face, and elastic face weren't able to do too well on the DLOT problem. And here are the results of the proposed segment, where at different distances, so whether it is 5 meter to 15 meter, whether it is different kinds of accessories like sunglasses or masks, or if you take the combined overall data, we were able to get significantly better performance compared to what other state-of-the-art models were doing, right? So even with respect to different segmentation techniques, these are the results that we got, that if you analyze the performance on the results on the verification performance, it could focus on the important regions of the face rather than just focusing on non-important regions or other regions. For example, in this case, the mask was occluded, but it could focus on, in this case, only the forehead region was visible, so it could focus on the forehead region. We also compared the performance of dropout, of different dropout techniques that are there. So in terms of different dropout techniques, if you have no dropout versus the different types of dropout, we could see that the performance with SegDGNet worked significantly well at different resolutions from 128 plus 128 to 16 plus 16 resolution as well, right? Now, this was good. We published this paper, we published a few papers on this, filed a patent, and one fine day, we got a call from one of the ministries regarding the Odisha train accident. So I'm sure all of you remember in June, there 3 trains collided, and there were a number of people who died because of those train accidents, right? Now, in that, what had happened was there were 260 people who were killed and more than 1,000 were injured in the crash. The challenge was that many of the dead bodies that were there, they were not able to identify the dead bodies. We don't have major fingerprint or iris recognition data, and the time was passing. With passing time, the bodies were decomposing, degrading, all of that was happening. So how do you recognize these bodies? They contacted Aadhaar, but it would have taken a bit more time because we don't have access to Aadhaar data. So they reached out to us. We had been working in face recognition for a while, so they reached out to us that can you do something about this, right? Now, injured face recognition is a problem that we had started working back in 2018. When we started working on that, even though there are a lot of injuries every day on roads in other places, for example, 1.25 million people are killed and 50 million are injured, the staggering statistics of road accidents and other accidents, right? But there was no data set. So, and this is, as you can imagine, creating a data set of injuries, facial injuries is a very difficult problem. If you go to hospitals where there are a lot of patients go, there are challenges with privacy and other challenges. So at that point in time, in 2018, 2019, we had created a small data set, whatever we could gather on the internet, just 150 subjects. Right? We worked on this problem, and propose some algorithms at that point in time. And as you can imagine, the problem is really challenging with injuries. Right? There are different kinds of injuries, and there are patients. And the injuries look consistent more than the faces that we get. So the standard challenges of interclass variation, interclass similarity. Right? Now, when we have this, we thought when they approached, we had this information, we had this model. We thought, what if we consider the injuries and occlusions? If we consider the injuries and occlusions and use our face model that we trained for occlusion, can we do something about it? So they gave us the Ministry of Electronics, Ministry of Railways, they kind of, sorry, Ministry of Telecom and Railways. They gave us the data, the face images of people who had died, that was given to us. I'm sorry for the graphic images. These are the real images from the site that were given to us for formatting. And they, using this mobile triangulation technique, they identified a set of people who were there on the, who were likely candidates to be there on the train. When you do the reservation, they give phone numbers, right? Not always is the phone number correct. Right? That I might do reservation for one of my relatives, and I always give them. So they use that data for the train reservation, and then use mobile triangulation technique to see which are the numbers that were the part of the train or that were there at the that were being used at the accident. So this department, this ministry did something to give us a candidate of 500 plus likely images that these individuals could belong to, right? So this was one of the hardest cases that we had to solve, because as you can imagine, even the face detection for half the images was not working. So students had to sometimes manually annotate and get the ground truths. So we combined this mobile gallery data, and this is what was used to get us the images. And we were asked to provide top tier possible matches. So we used this matcher that we had created. We considered different injuries as different occlusions and tried to get multiple versions of our model itself and try to get correct matches, top K best matches. And these are some of the results that you actually see on the slide. So for this gallery image, these were the possible faces that we could get. Look at the differences that are there from the actual probe image to the gallery. It's difficult for people like us also to recognize them. For algorithms, you can see the challenge that could have been there, right? But students worked straight for 18-20 hours because it was the third day that we got the images, and they were really time pressed. So we were able to identify 120 unclaimed dead bodies using the approach in less than 18 hours. And what gave us a lot of satisfaction was we were able to give closure to these many families. Others we could not go. We are not sure whether it is containing the correct set of images or what happened, but these 120 cases were correctly solved. So what it does is all of these algorithms that we face recognition algorithms that we talk about, right? Surveillance is a constraint and all of that. But this opens up a real new threat with opportunity to assist government agencies and other agencies to help or identify in such conditions. We don't have these DNA data sets or our others. Long back when the tsunami hit, there was a tsunami in Indonesia. So Indonesia has a very strong dental data set for all its residents. We don't have that. So all the data sets that we have are kind of, so dental doesn't change with time, right? Even with dead bodies, you can find that. But in this case, there was a challenge. So we need to come up with metrics to identify these people, identify the dead bodies in cases in such calamities or incidents. So this was with respect to face recognition that I wanted to discuss with you. Very few researchers across the globe are working on challenges like this, but as far as we think, we need more of these approaches, right? And the second thing I wanted to discuss with you today is the work that we're doing with respect to deepfake detection. I'm going a bit faster because of the time the chairperson has given me to finish in time. But if you are interested in details, you can approach me later as well. So deepfake is something we all know, right? Anybody who doesn't know deepfakes, fake news we are aware of, right? So deepfakes it's a major problem today, right? This is this generative AI generative AI itself. It's a very positive thing. We are able to create a lot of different things. Students are using generative AI to write their papers. I get a lot of time paper written with very nice abstracts, introductions and stuff. I see students laughing right now. I'm assuming it's because of that. So, but when you see what it is doing, you could very clearly see that this is written by ChatGPT, not by students. It's amazing quality of English and sometimes hypothetical references, all of that comes. It's not the work of students. See, some of those is good, but then there are problems as well. What are the problems? This is one major problem that comes because of it. There is a discussion that, okay, so I'll come to that later. Just I think all of you know President NASCOM. She visited Jodhpur some time back, and we had an opportunity, my lab had an opportunity to present to her. And we have permission to create these papers. Can you please switch on the audio? So, you know the lady in the first video that is currently playing? Anybody? This is Neetam. So this is a video of me. Translation. Yeah. No, it's okay. It's okay.
Purely indeed a privilege to be here today. On the same platform as some of the most accomplished women from India and from around the world. To speak unto such wonderful women and sometimes we overwhelmed.
So the original video, the first video, the original video, right? What we did was we used space images of Mr. Janet Bush to create a deepfake of her, right? So instead of what Neeta Amani is saying, that Janet Bush is saying the exact same thing in her voice with her face, which is kind of in deepfake terminology or in image processing terminology overlaid on her face, right? Now, this was a reasonable quality image. We did not have too many images of Deljani like that. We did what we could. So just using that, we created this video. Okay, now let me show you the other one. Listen to this video. So this is the first audio. Okay, so these are the two audios. One is real, one is fake. In something this is real, this is fake. This is fake. Okay. Okay, now we have two things. Which one is, so the song is sung by, the song is originally sung by Arjit. The second one is, the second one is good. There's one here and Vijay, then
Personally, nothing.
so what they're talking of the thing because it's not used to sing other songs. That people of not completely agent. So what we did, we have this amazing song. We this is not created by us. This is available in YouTube. Somebody is down here. They took a long video of 20 minutes of advertisement. I'm going to say this. Now this is one example. Now when people are like you and me, we come to culture. Now imagine the misuse of this. It is you can just anybody say anything. People sing each other's song, people making any kinds of claims, with elections coming very close, even governments are concerned. And we keep getting a lot of images and videos of this kind from law enforcement agencies. Can you please check for me if this is real or not? Right? So that is, it's a very valid problem, which is not only being faced by high-profile people, celebrities, politicians, but it is actually affecting regular people like you and me, right? What is happening? Imitating people's speech patterns possibly to bring trouble, right? We just discussed. Violating women by forging nudes from regular pics. You can do that, right? There was a fake image in May of Pentagon bombing that came up on Twitter, and within minutes, the market was affected, right? Within minutes, they could also identify that it is fake. Nothing of that sort is there, and there were declarations that this is not. But this within those few minutes, there was a lot of hue and cry about it, right? After 2.5 years, Kerala women wins battle against fake news video, and these are not celebrities. These are regular people that are getting infected by it. So we need to do something, right? So why is this a problem? The problem is because the quality of deepfakes is increasing day by day, and generative AI's power is increasing. The quality of these videos is increasing, right? So the difference between real and deepfake is getting blurred. And the second reason is there's a lot of compression that happens. All of these videos, they get circulated on social media, WhatsApp, all of these places, right? And when you circulate on social media and these communication channels, you don't circulate high resolution videos. We generally send low resolution videos. So there's a lot of compression and different types of compression that goes in. WhatsApp would be doing something else, Gmail is doing something else, Twitter, Facebook, all of them are doing different kinds of compression. So identifying these deepfakes with and without compression, right? You need an algorithm, and you won't know whether it is actually compressed or not. And using what kind of deepfake generation algorithm has been generated. So there are CNNs, there are GANs, there are diffusion models, all this is a huge class, different types of models that are being used today, right? So these are some of the deepfakes with and without compression that you see here, and there are different degrees of compression that can be applied, right? And this is the result. So conventional images, these normal images without any compression, detecting deepfake, basic algorithms were doing like 80%, 85%. But when you have compressed images, so this is raw and orange is compressed, there's almost a 20% dip in the performance. So what we need is high performance and high quality images, but this is what the problem is, low performance with compressed images. So we started working on this and we analyzed a lot of images to see if there are artifacts which are visible. Earlier algorithms that were there, deepfake generation algorithms, you could see the artifacts, but not anymore. They're very, very clear, very nice, right? So visible artifacts are very difficult to identify. So we thought there must be some signature that these deepfake generation algorithms are leaving the images. So we found those invisible signatures, invisible matrix, or right. So we used a uniform visibility, the concept of uniform visibility matrix, where we actually learned that across different kinds of deepfake generation algorithms, what are the pixels that are getting updated? What are the kind of changes that are happening? So first, it's a kind of a two-step algorithm. The first is this learning of visibility matrix. Like what are the changes that are happening, right? And once we learn what are the changes that are happening, we accentuated those changes and created a data set with those changes accentuated of that deepfake was bringing. And we did then a deepfake detection model where we combined the data set that we have, original data of deepfake in real, along with the augmented data from this visibility and training matrix. Some of these questions are there in the paper and we can discuss it offline. But this is what the visibility matrix is something looks like this. The completely random image at the face of it, but it doesn't input the changes that are happening with deepfake with deepfake generation. And in terms of deepfake, there are two things that you can do. You can create exactly from noise, deepfake from noise, or you can input a image. And you can just change, you can do face swap, or you could change some of the attributes of it. For example, hairstyles, expressions, those sort of things. So the challenge is across all of this, even if it's generated from noise or if it is generated from original image deepfake, you should be able to recognize it, right? Now, once we had this algorithm, we tested it on several different face data sets, deepfake data sets that exist in the community. And we tested with intra-compression as well as intercompression. Now look at the visibility metric. The space images you won't look, they're very off, but there is a bit of irregularity in the chin region. If you look very closely, a high resolution image, you'll see there is a irregularity in the visibility matrix that is there. Right? So we try to learn that and using the algorithms that are there, and we train models in terms of intercompression as well as intra-compression. So the model could be trained with no compression, but see if it works without compression as well. Right? And these are some of the results that are there that we were able to achieve. Now, the interesting part of it is the deep learning model could be any of these models. What we changed in the setup, the framework that we proposed, that framework was learning this visibility matrix. And this visibility matrix could be learned with different kinds of model as well. So we tried with two exception rate and less than 50, and these are the results. So intercompression and intracompression, and you could see the significant improvements in the performance that, I mean, even with compression, C23 or C40. So C23 is compression level, 92%. But if you increase the level of compression, we were able to do close to 70%, 78%. Then it is just trained on zero compression. Now, if you train it on all the training data, use both compressed as well as real images, we were able to do more than 90% across the entire training data, across the entire test data, right? These are the results on some public figures in some public figures that are available. So these are the deepfakes that have been generated by other folks, right? Yeah, and they were quite popular on the social media. So we were able to detect all of them correctly. And one of the challenges that we observed is all the data sets that existed, none of them pertain to the Indian community. So all of them had Caucasian individuals in the data set. And as you might have seen, AI bias, there has been a lot of discussion on AI bias due to skin color and other challenges. So we created this, at the end of the day, if you're working with Indian setup, our models need to be able to properly detect Indian faces as well, deepfakes and Indian faces as well, right? So we created this multi-subject heterogeneous data set, termed it as the platter. It has more than 130,000 videos from multiple doctoring types, and a lot of different challenges we introduced. This published in 2023, and the data set is available. We also in this introduced for the very first time multiple people in the same deepfake. Till now, if you look at all the previous data sets, they had a single person in the data set. So you could have images for partial deepfakes. So what I could do was, we are sitting here. Now, if I want, I can introduce one person in one of the seats. Rest the entire image is original, only one person is changed. Right? So even that kind of a problem where there is majority real or majority fake, some part is real, that's called as partial deepfake. So how do you recognize or how do you identify it? So we introduced that challenge also, and we are currently working on it. To discuss the impact of this, like I said earlier, right? It's not only the celebrities and other people who are affected by it. This tool has been, the tool that we developed has been given to several law enforcement agencies in the country, right? And several such cases have come to us to the result. But I just mentioned one specific case that happened in one of the villages of the country, that there a pornographic clip of a girl from the village was circulated in the village itself. Now you would imagine AI deepfake. A small village person might not know this, but that is not true anymore. And this is a very we would say a very standard story that happens. That is a high profile boy, low profile girl, and all that. So this is what happened. Advances were rejected by the girl. He created a pornographic image, and the panchayat of that village actually disbarred the family on a deepfake being circulated. So the law enforcement agencies actually took it to use that tool to analyze it, and they observed that it is giving it as a deepfake with the explainability and all of that included. So they use that to talk to panchayat again, explain them all of it, and then it's when the disbarment was taken back by the panchayat, right? So it has significant implications at all levels right now. And so this is what we are doing, trying to build responsible systems. But as far as I see, it's a cat and a mouse game. You do whatever you could, and then there's always the attackers who be there to champion further, right? These are some of the students and sponsors that I have. Sorry. Uh, this is the specific team that has worked on the face recognition in the deepfake challenge. The face recognition was sponsored by Day1 and Swiggy, whereas this deepfake research was sponsored by Ministry of Home Affairs. So with that, thank you very much for patiently listening to me.
Thank you, Richa, for keeping time. We have a couple of questions. Time for a couple of questions. Anyone from the audience? Not from the first room.
And incorporated this in social
Picture extraction aspects of for the deepfake detection. So, and the deepfake is that the smooth video or audio generated via deep learning method. So, either in video, that is in images, or I mean the computer that is speech. We say that there are features which may not be perfectly relevant, or they are but they are irrelevant. Video, video extraction. Usually, active speech, active audio, active video.
It can be. Right now, what we are doing is more to deep learning skills and trying to have really subtle variation. It's something that is differentiating a little bit, but actually, but what we're trying to differentiate is the species, the detection of. But what you are saying is definitely possible, and you need a complicated finding metric, the uncounting as well the deep learning. So that is important to differentiate between, is it? So in these cases, we have not seen converted the recognition. This is done irrespective of the recognition. So whether that is important or not, that doesn't clear.
The deepfake data, but corresponding the data is not there. The picture extraction versus the classification model using deep learning. In the deepfake case, which are the negations?
There is one of the papers in the beginning when we take people started and we can papers where we employed pretty big. But they were very big. The class of fake is fixed. Right? But today you must want. We want these models to be generalized. It's like a virus independence. What you build, the most you need to when you buy something, you have to completely change. Then what you be extremely constant. You want this need that you to be able to go. So that is not currently happening. So in what we want to use motion. So they have to use the book to take this review. We pay for what is video pay. Money is very expensive in the way. So it has to be if you real pay. We have to I'm thinking, but
defined. This is physical constraint, facial features that is based. But when you create a deepfake, that's like change that you call in the change region there, that change is changing. Because when you input that video to a motion magnification words, the change in the change there, which kind of gives you a clue that something is wrong. This thing should be deepfake. These unwanted variations that will help you for better deepfake. So that is one thing that we are trying to do, which is not really uncrafted features, but it's concept. There's domain concept that domain context and so on. But don't blindly get another way, information in those things.
Thank you very much.
Thank you. That's the.
The limitation of face recognition. So given the limitations, so what are the chances of, is there any data on that? If an actor wants to impersonate someone and identify to break a security system or to be identified as someone else, what is the data of percentage given the current advancement, the current models that we have of face recognition?
That's an interesting question, and the answer to it is it depends on the level of business. So I think working for a while is disguise, recognizing disguise statements. So if you have some really good experts that make up experts and other classes who see what is right for you, it is much good. So we have done a few images what we did was take a look at Amitabh Bachchan or Richa Bachchan. The people clear a form that is the next level of design building. Award also. And they are which goes to the human context. We know these personalities, but also we want to but
And even if I know when you model even the other patient ask that I will provide the person from the team. So if I know that the system tries to system I can write the rule identity and that increase the level of the level of accuracy that increase.
if you more features, if 75% of your face is included, which includes eyes and features below like this view. Then it is bound to affect face recognition system in a way because then only what has been delivered. How discriminating is the correct thing. Right?
So this goes against like the more you are trying to facial is actually it is making it easier for knowledge that this itself is identifying muted facial. I think that I'm very
If you know what so that is what saying that the right what we are doing is not really use it, but we so to give you an example, if Dr. Chandra is walking on stage, you don't need to say his face. You can probably recognize him from the house. So I will give one kind of example. I was thinking, what is the So I because TV, especially okay, they expect to see them in that. Okay, so we have to create a lot of content.
Yes.
So make it integrate this context information in the process. I think that is very important. Yes. You only have to go away. Which should is this.
Okay. This is the last question because all are hungry. Okay, please come on.
Speaking about restricting the deep fakes and so as you interact with different stakeholders, how do you see impact of different things? These restrictions on deep fakes?
That's why I know in fact he is thinking that it being identified so I think what is the time stop the defect from spreading. So we are even trying to protect the identity of the then you take that but then you take this into very very big. Can you protect the if it is only if it is negative, to stop it there. So these are some of the that we are
Thank you, Richa, for nice talk. And your talk has created lots of interest and praise among the audience. Last question. Okay.
Diffusion model is what we so diffusion model is what we we were talking here, but because you say that
Okay. This is almost the end of the session, and before that, we like to present it.
I would like to request Professor Chandu to please felicitate Professor Singh with a memento. I would request Professor Malay Kumar Kundu to please come up on stage and felicitate Professor Chandu with a memento.
Okay, June.
So we take a break and lunch packets have been arranged in the backyard of Kolmogorov Bhavan. Now post lunch, we have 3 parallel technical sessions, one here at PJB and 2 other NAB1 and NAB2 of Kolmogorov Bhavan. The speakers of the tutorial session are requested to reach out technical session. The speakers of the technical session are requested to reach to their respective venues 15 minutes beforehand, so 1:45 p.m. So we can have your presentations ready with you in your pen drive and submit it to the respective there.